Starts off slow. Okay, now it's the sort of thing that you've seen skaters do, I'm sure, on television, where they go into this spin. But has it ever occurred to you, how come they speed up? There's nobody pulling them with a string like a gyroscope. Come back. Anyway. But why is it that she speeds up? Okay, so by bringing her mass, her arms and her legs close in, what is she actually achieving? Okay, so she's reducing the moment of inertia. So she starts out here with the leg and her head out high, as much mass as far away as possible from the angle of the center of rotation, brings everything in, tries to become just a thin vertical rod almost by bringing her hands in, and she's speeding up. What we'll come back to later on this morning is there is actually an increase in rotational kinetic energy. She's changed the moment of inertia. There's no external torque, there's no external forces here, yet astonishingly she's managed to speed herself up. No force exerted on the ice, all she's doing is spinning on a frictionless surface. She's managed to speed up. Angular momentum. So we're just going to look at what angular momentum is and how you calculate it. Because angular momentum starts to explain a lot of the very interesting things about why things can actually speed up and slow down when they are rotating. Angular momentum is defined as being the moment of the momentum of a mass around a center. So if you've got something that's got a mass m, radius r, traveling with speed v, it's got a linear momentum of m times v, that much you know. But the angular momentum is defined as being mvr. So it's really the moment of the momentum as something's going around. Now if we've got that rotating at omega radians per second, can we express that in terms of omega? So we need to work between v and omega. What's the relationship between v and omega? No? Okay, so we can substitute in v equals r omega. So that's going to be r omega times r, which gives us m r squared omega for the angular momentum. Angular momentum has got a symbol capital L. It's just the letter that they use. So the angular momentum is mr squared omega. Mr squared, that sounds familiar. For a particle of mass m rotating radius r. Jonathan, how's that familiar? Okay, so we've got moment of inertia. So L is actually equal to I omega. That actually looks very comforting, even though it's a brand new equation that you've never seen before in your life, and it's one that you'll need to use and learn. How is that kind of comforting? What could you compare that to in linear motion? Okay, so for linear momentum, which has a symbol P, is equal to mass times velocity from something moving in a straight line. That's what linear momentum is. In rotational dynamics, the angular momentum is moment of inertia times the rotational or angular velocity. So your moment of inertia, what would the units be for moment of inertia, Andrew? Okay, so you've got kg meter squared. That's got radians seconds. So angular momentum, it's got a right mouthful of units, but it is in fact going to be kg m squared radians seconds to minus 1. Kilogram meter squared radians seconds per second is the units of angular momentum. An angular momentum as a quantity, you could calculate the angular momentum for, say, a bicycle wheel turning. It doesn't really have much relevance, just in the same way that momentum of an object didn't really have much relevance until something started happening. What made momentum a more interesting concept at higher? When did you really have to start calculating momentum? Yeah, in collisions. Where you had collisions, that was where, because the momentum was conserved, then we needed to calculate the total momentum before and the total momentum afterwards. So I'm just going to show you what happens in the case of conservation of momentum, where we've got the momentum before and the momentum afterwards, and in terms of rotational momentum. I'm going to increase the moment of inertia of the turntable, and I'm going to do it in a fairly unsubtle kind of way, just by plonking some masses on like that. That's got more moment of inertia than that has. So we've started off there, so that's got a low moment of inertia, high angular velocity, increase the moment of inertia. What happened to the angular velocity? Yeah, decreased. So there's a bit of evidence for conservation of angular momentum. So there is some evidence there for conservation of angular momentum. It is just a fundamental law which you could explore. It's quite a difficult one to set up experimentally, because you've got to somehow change the distribution of mass in the rotating system. Now, as I said, we did it pretty unsubtly just by putting in extra mass with that sort of radius. What could we have done with this as it was rotating? Say if we started it like that, how could we have changed the moment of inertia of the system? Yeah, so we would need two small mice or something actually on the rotating disc and tell them, right, you pull that one, and change the rotation, change the moment of inertia by changing the distribution of the mass. The other thing you can do is that you can have these wrapped around a string, wrapped around a rod, so as the string wraps further and further round, they pull each other in. So we'll maybe try that later just to see how it works. But so in terms of conservation of angular momentum, the law of conservation of angular momentum is just as it sounds. It's just the total momentum before equals the total angular momentum afterwards. And I'll show you how that explains the skater in a moment. But if you just add that in. So there was always a sort of there was always a proviso with the conservation of linear momentum last year that it had to be in the absence of any external forces. What would be the proviso in the case of angular momentum? What will it need to be in the absence of? External, not so much forces, but again we're thinking about twisting, turning, rotation. So instead of force, we're thinking more, what's the rotational version of force? Torque. Okay, so in the absence of any external torques, so the total angular momentum before equals the total angular momentum afterwards. That means you've got to add in all the various bits of it. If there's new masses that are attached to the rotating object, that's going to change its moment of inertia. There is a simpler way to write it, of course, just that I1 omega 1 equals I2 omega 2. Moment of inertia initially times that initial angular velocity equals the second moment of inertia times the second angular velocity. In the case that we've just seen with the masses there, had a small moment of inertia times a high angular velocity, that then equaled a much bigger moment of inertia, I2, times a much smaller angular velocity. So if you double the moment of inertia, you'll halve the angular velocity. Triple the moment of inertia, you'll make it by a third the angular velocity. Still doesn't explain the skater, but we'll come back to that in a moment. Just have a go at this. So we started off like that, and once I let go of it, there's no external force, no external torque. Firstly, what do you observe happening? Okay, so is that the linear speed or the rotational speed? Okay. It's actually quite difficult to work out to the linear speed because it's going at a larger radius. So it's possibly going faster out here. But it's certainly the omega, the rate at which it goes is increased. But what's the explanation? Why does it appear to increase the omega? Hey? Go on, Star, say it again.
Because it's still going at the same speed. Well, it's relatively similar speed, but it's because the radius is smaller.
Okay, got a smaller radius. So what's that going to affect in the system? It'd certainly be going around a smaller circumference, but in terms of angular momentum, which two of those things will the smaller radius affect? It's the same mass. Yeah, so a smaller moment of inertia. So if you've got a smaller moment of inertia, what's going to happen to omega? Yeah, so that's why it speeds up. Because I've applied no external torque to it, so it just goes faster and faster because of the conservation of angular momentum.